Today we're doing nukes. We're starting on nukes. We got 3 days of nukes. A nuke is a kind of radioactivity. It's based on a kind of radioactivity. If you look on the chart, you find there are these two elements that are particularly interesting. One of them is called uranium. It's found in nature. There it is, element number 92. So that means it has 92 electrons. Uranium has this, again, think of a flea or a mosquito in the midst of Memorial Stadium. And there's the nucleus. And it has 92 protons. It's uranium-238. What that means with 238, that's called the atomic weight. Now, all the weight is in the neutrons and in the protons. But if you subtract 92 from this, you find 6 and then 4, 146 neutrons. It has that many protons, that many neutrons. The neutrons have no electric charge, but they serve as a glue. At the same time, you put too many of them in there, or you don't put them in the right place, and the nucleus can become radioactive. This is radioactive. Uranium-238 is radioactive with a half-life of, actually I forget, it's billions of years. I do remember uranium-235. Let's look at uranium-235. What's the difference? It's still uranium. That means it still has 92 electrons. It's still uranium. That means it still has 92 protons. These little mosquito-like things in the center that have all of the mass. A proton weighs about 2,000 times as much as an electron. So an electron is there. It does have some mass, but it's really tiny. 92 protons. So, but it has 3 fewer neutrons. That's 143 neutrons. Turns out uranium-235 is radioactive. It has a half-life of about 1 billion years. Go back to the beginning of the solar system, and there was lots of this stuff. It was abundant. And then it started decaying. After 1 billion years, there was only 1/2 as much. After another billion years, only half of that. After another billion years, only half of that. After another billion years, only half of that. And here we are. And so it turns out that uranium-235 is about 0.7% of your ordinary uranium, just because it's mostly decayed away. This is decayed away too, but it has a longer half-life, so not much of it is gone. Other things have shorter half-lives, and they've gone even faster. Now, there's something very special about uranium-235, and there's one other. So this is called an isotope. Basically, it's uranium. It has the same number of electrons, so the same chemistry. If you want to do chemistry with uranium, it doesn't matter which one you have. They behave the same way. One weighs a little bit more, but you hardly notice that. In chemistry, the weight doesn't matter that much. It's mostly the electrons. So these are called different isotopes. And we can say, here's one isotope of uranium, here's another. This one is a rare isotope, not really rare, 0.7%. That's not tiny rare. It's enough there so you can do something with it. Then there's another element. This is one called plutonium. It's over here. It's done in light colors. That's because it doesn't exist naturally. It turns out cosmic rays and radioactive decay can produce tiny little bits of it, but basically it's not there. It was first produced here on this campus by Glenn Seaborg. Glenn Seaborg had Seaborgium named after him a while later. Where's Seaborgium? There's element 106, Seaborgium. Okay, he discovered plutonium. He did that here. And he had to make it from other lighter elements by adding neutrons, getting decays, and so on, putting it together. He found this plutonium. Plutonium-239 is a very interesting one. There's another one, plutonium-238, which is actually harder to make. This one has a half-life of 24,000 years. That's a number that comes up so often in the news. You'll hear it cited over and over again. I want you to know that number, just because it turns out to be news-wise an important number. You'll hear it cited when people talk about nuclear waste storage. You reading the newspaper? Okay, good. Because this is important stuff. This is the lecture that you'll probably use more than any other. Well, I don't know. I said that several times. Plutonium-238, which has one less neutron, has a property that its half-life is 80 years. Not only that, but its radioactive decay is alpha particles. Alpha particles are really nice. See, they don't even get through your skin as long as you don't breathe them in. And so plutonium-238 is produced in a special way, and we used it in our probe that was launched just a couple weeks ago to go to Pluto. Why? Because it decays so rapidly that it has lots of energy. It heats it up, gets very hot. You can turn that heat with something called a thermocouple into electricity. So the power to broadcast back when you're way away in Pluto, it takes 10 years to get there. This stuff will still be producing a couple hundred watts of electricity so it can broadcast things back. Really nice for space. It used to be illegal. Why was it illegal? Because it was plutonium. And plutonium was considered really super dangerous by the public, even though the experts knew it was quite safe. And so laws were passed, you cannot use this kind of stuff, can't send it into space, what if it crashes, and so on. There was a lot of, I think, harm done by the fact that people's fear of plutonium meant that people would pass laws making it illegal, when in fact it was really quite harmless. Fortunately, we're beyond that now, and this plutonium is being used. But these are the famous ones, uranium-235 and plutonium-239. This has a half-life of about 1 billion years. But they both share a property that is key to the rest of this lecture. And that's the following. Suppose you have a neutron coming from somewhere. You can make a neutron. There are several ways to make a neutron. One favorite way is to take something that's radioactive and produce alpha particles. So we have a bunch here of atoms. You have a little bit of polonium-210 or something like this. It's radioactive and alphas come out. Now you put a little beryllium next to it. And it turns out that when an alpha particle hits a beryllium nucleus, a neutron shoots out. So boom, out comes a neutron. This is a way of making neutrons. It's actually a very convenient way. And you'll see one of the atomic bomb designs, atomic bomb design I will show you, has a little thing in the middle to make neutrons to make the bomb work. And all it does is it takes the alpha particles and a little beryllium, and they're sitting there happy as can be. The alphas are coming out. They don't go very far. Then you bring these things together, and suddenly the alphas hit the beryllium, out come neutrons. So you can make neutrons that way. You're not making them. You're releasing them from the nucleus. The alpha particle bangs into the beryllium, and out comes a neutron. If that neutron comes to uranium and hits the nucleus, it could stick to the nucleus. Certain probability it will stick. If it does that, we no longer have uranium-235. We have uranium-236. Now, here's the key feature of uranium-236. It becomes highly radioactive. Its half-life, the number is probably less than 1 billionth of a second. I don't remember what the number is. And it doesn't just give off an alpha particle. It explodes with something called fission. The nucleus breaks into 2 pieces and they go flying apart. They're repelling each other. Once it breaks, once that nuclear force is broken by that extra neutron going in just the wrong place, the 2 sides break apart. We get these 2 pieces flying out. The pieces that come flying out are called fission fragments. Now, you take any nucleus and break it up into 2 random pieces, and the odds are those fission fragments will be radioactive. And in fact, most fission fragments are radioactive. That's called the nuclear debris or the nuclear waste. So that's the origin of the nuclear waste. We're going to be talking a lot about nuclear waste. You will read a lot about nuclear waste. Oh, by the way, homework is due tonight. But again, it's a practice exam. Pick an essay exam and answer it. We had lots of essays posted on the typical exam questions. Send it to your GSI in the normal way. So make sure you do your homework tonight. But anyway, a neutron comes in here. It doesn't smash it apart. This thing is almost coming apart anyway. It's held together by the nuclear forces. That neutron comes in there and just unbalances those nuclear forces in such a way that this thing flies apart immediately into two pieces. The pieces are different sizes. The stuff that comes out, because it's random pieces of nuclear material. Remember, in the early solar system, almost everything was radioactive because they were just random pieces of junk. Of course, the stuff that's radioactive isn't here anymore. So mostly we're left with either things that aren't radioactive, like ordinary carbon, or things that are radioactive with really long half-lives, like potassium-40. But if you just break up a nucleus, the pieces are probably radioactive, and most of them are, and this stuff is bad. It leads to two things. One is nuclear fallout. The other is nuclear waste. So these are two issues that are going to be coming up over and over again in these lectures. But that's where they come from. Plutonium, the same way. What happens is if a neutron hits this, by the way, it's not easy to get a neutron to hit the nucleus. Think of it. It's like shooting a bullet into Memorial Stadium and trying to hit that mosquito. Most of the time you miss. But when you do hit, the mosquito breaks up, releases enormous energy, and you get two fission fragments. Fission fragments, radioactive debris, that's very dangerous. Leads to nuclear waste and nuclear fallout. Now, here's the discovery that makes this thing suddenly exciting, fearsome, dangerous, useful. Not only do you get two fission fragments coming about, but on average from the uranium, you get two neutrons coming out too. Plutonium, you get three neutrons coming out on average. When this was discovered, it was seen as the key to the chain reaction. A chain reaction is, well, you got this thing, and you send one neutron in. You can get the neutron from beryllium. This thing fissions, out come two neutrons. Suppose you put enough uranium around here. Well, you have to put a lot because it misses most of the nuclei, right? So if I just have one next to it, it'll probably miss. It's like hitting a mosquito in Memorial Stadium. So you put more and more and more and more, and you put enough of them in there so that it's likely to hit. If you do that, that's called a critical mass. A critical mass is when you put enough material there that it's likely to hit. And you see, the word critical mass actually depends on lots of things. I mean, suppose you have a critical mass and it looks like this. It's not a critical mass anymore because the neutrons will fly out and they're not going to hit anything. So it's not just a matter of the mass. You have to kind of put it into a sphere to really make it into a critical mass so that there's no way you can fly out without hitting something. You can't have it long and thin. The geometry matters. There's another thing. Suppose you compress it and take the same thing and push it into a small, tight bundle. Well, think of the atoms. Here you are in the middle, and you're looking out, and you see the stars. Those are the other atoms. You wonder, if I go off in that direction, will I hit one? If you compress them and bring them really close and tight, the space between them is much smaller, you're more likely to hit it. So the critical mass depends on whether you've compressed it or not. So when we say the critical mass of something, you have to recognize it's not just so many kilograms. It's also the geometry. The first atomic bomb on Hiroshima worked in the following way. Two pieces, I don't actually know what the shape of the pieces was, but let's just assume it's a hemisphere like this. Each piece was less than a critical mass. What that means is on the average, a neutron would come out. It might hit, it might not, but on the average, you know, it would go. I mean, it would leak out. This was put inside of a gun. It's called a gun design. An ordinary explosive, not gunpowder, but probably something called a high explosive was put in here. And it actually wasn't done with a fuse. You know, it was electronic ignition. What would they do? This thing was dropped over Hiroshima by the Enola Gay airplane. There was a second airplane flying over Hiroshima from the US military. was carrying my thesis advisor, Louis Alvarez. Louis Alvarez was flying over Hiroshima at the time the bomb was dropped. He told me all sorts of stories about this because he was given the job of measuring how big the explosion was. And here's what happened. This bomb was dropped off a parachute. By the way, a little story about Hiroshima. Hiroshima was an undamaged city. Most of the cities of Japan had been destroyed. Hiroshima had not been. Interesting reason why not. The only reason they had not previously destroyed Hiroshima was that they were saving it for the nuclear bomb. They wanted to have a city that was untouched, so there would be no question they could examine it and find out how much damage was done by the nuclear bomb itself. Same thing was true of Nagasaki. These were two cities that were chosen as important cities to bomb, but they had not been bombed throughout most of the war. This was dropped. It's called a gun design. You can find photos of, they gave it a nickname. They called it Little Boy. They had two bombs. They had two bombs, and only two bombs. At the time they dropped this. Dropped down on a parachute. Once it was above the city, I'm not sure 1,000 feet or just how above, they detonated it in the air. They did that because this does maximum damage. This way you have line of sight to more. If you do it down the ground, you don't get as much damage as if you do it in the air. They figured out the most damaging altitude to do it. The way it worked was they detonated the high explosive. This piece went flying towards this piece. When they came together, you had a critical mass. At that point, you had two pieces that when a neutron came, and I don't know whether they used this trick to get neutrons. I think they might have. They had one piece with alpha particles on it, and the other with beryllium. So when they come together, suddenly you get some neutrons. Now this neutron goes and causes a fission. Out come two neutrons. Each one of those causes a fission, 2, 4. And now you ask, how many times do you have to double? You go from 1 to 2 to 4, 8, 16, 32, 64, 128, 256, 512. After 10 additional steps, you're up 1,000. A factor of 1,000. That's after 10 steps. 2 to the 8th. Is it 1,000? 9 steps. Wait. Start with 1. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,000. So 10 steps. 2 to the 10th is 1,000. 10 steps later, you have another factor of 1,000 in the number of neutrons. You have 1,000,000. That's another 10 steps. Another 10 steps, you have 1,000,000,000. Another 10 steps, you have 1,000,000,000,000. By the time you get up to about 75 steps, you have Avogadro's number. That means basically every nucleus in that uranium has fissioned and released its energy. The energy being 1,000,000 times greater than an equal weight of TNT. So there's your atomic bomb. That's how it works. Use this doubling. Now, of course, there is a problem. Once this thing, what's happening is that when you get the fission, these fission fragments are flying out. And they have a lot of energy. It's kinetic energy. They collide into things and they heat everything up. So what you're really doing is turning this into heat. What the atomic bomb is really doing is taking that nuclear energy and creating a huge amount of heat. Now here we're going, 1 billionth of a second, 2 billionths of a second, 3 billionths of a second. These things are probably doubling every 10 billionths of a second. They double, 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 double. You get to a certain point where now you have the same energy density as dynamite. At that point, the thing blows itself apart. And it stops. Well, that's no good. That's like dynamite. You could have dropped dynamite. So what's the secret? The secret is that the neutrons are going really, really fast. You get up to the level of dynamite, this stuff is all heated, it's starting to blow itself apart, and here it goes, it blows itself apart. But meanwhile, the neutrons are going real fast, they're doubling, 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 and before it blows itself apart, you release even more energy. So that's the trick of the atomic bomb. It's one of the tricks, is you use these fast, super fast neutrons, so the doubling takes place a lot faster than the blowing itself apart. Finally, it gets up, where all the energy is released, and at that point, you wait around for the thing to blow itself apart. And what do you get? Well, you get several things. One is you get that enormous energy of the blast. That's largely heat. And the heat goes to this big explosion. That's what killed most of the people. Estimates of from 50 to 150,000 people died in Hiroshima. We don't really know the answer because there wasn't that much left. So it's mostly this huge energy release. Now, in addition, some of these fission fragments are radioactive. Plus, there's some radiation emitted. There are gamma rays that are emitted from this explosion. Also, some of the neutrons leak out. And these neutrons can also hurt people. But as you learned last week, the death from radiation and from radioactivity at Hiroshima was really quite small. Mostly it was the blast. You can't die of cancer if you're killed in a fireball. So that's what happened at Hiroshima. A few days later, over in Nagasaki, another bomb was dropped. It was not a uranium bomb. Here's the surprising thing about the uranium bomb, and this is really important if you want to understand terrorism, what's going on in Iraq, Iran, and North Korea. This bomb was never tested. Why wasn't it tested? Well, because we used up all the uranium we had. I say we. I was about 6 months old at the time. No, a year and a half. Used up basically all the uranium we had. Why? Because it turns out uranium is very, very hard to get. Uranium-235, as I'll explain, it has to be made out of uranium-235. Uranium-238 pollutes it. It keeps it from exploding. You have to purify it. You have to have almost pure uranium-235. And that was very hard to do. I'll be telling you that story in a moment. It was very hard to get uranium. Secondly, this thing is such a simple design. Everybody was pretty sure it would work. The design was easy. Look at it. I mean, there's stories that you'll see in the newspaper now and then. Some high school kid will get together and he'll draw this picture. Maybe he'll get it from one of the popular books that has it. And then he'll show his teacher, and the teacher will look at it and say, wow, let me call up the newspapers. I say, I had a high school student who designed a nuclear bomb. And they'll say, oh, really? Let's check that. So they'll take his sketch and they'll send it off to the Livermore Laboratory. And they'll talk to a bomb designer there and they'll say, would this thing work? And he'll look at the sketch and say, yeah, that'll work. And then the newspaper headline is, high school kid designs atom bomb. That's how these stories come about, by the way. You've probably heard them. You are now as educated as you need to be to compete with that headline. Muller's class at Berkeley teaches students how to design atomic bombs. So you could just imagine what fun people could have with that one. But that's it. Okay? Now, there's some details you have to get right, but they're not hard. And anybody who's worked with cannons can probably figure them out. Plus, you get someone who has some background in nuclear physics. Not hard to do. The hard part of the uranium bomb is getting the uranium. That's hard. Plutonium is different. Plutonium, it turned out, requires a much more sophisticated design. I talk about this a bit in the text. I may come back to it in a later lecture. But a plutonium bomb requires that you take that material and you compress it. The reason has to do with some pollutants that they could not easily get rid of in plutonium. Plutonium-240, it turns out, tends to pre-detonate the bomb. It makes it go off before it's completely assembled. So it turns out the compression is necessary. Here's what you need to know. What I want you to know is that a plutonium bomb requires an implosion. What that means is, you can make an implosion work with a uranium bomb too. Let me show you a design of an implosion bomb. Here's a nice design of an implosion bomb. Let me put this up there. If we could put on this, this thing. And so here's a, well, let me do it right side up. Let me zoom in. So here we have a somewhat detailed design. This is a little bit more impressive than you get from a typical high school student. This was done by a real expert. So let me zoom in. And a couple of interesting features about this bomb. It's round, of course. And the roundness is what you do for an implosion. What you want, an implosion means you surround this thing with explosives. So when the explosives go out, they also push this thing in and compress it. That's called an implosion. Very hard to do. Try squeezing a water balloon, you see the problem. You squeeze it here, it comes out between your fingers. So the implosion has to be exceedingly uniform. Very difficult to do. This is a somewhat sophisticated advanced design, uses what are called explosive lenses. We'll talk more about lenses when we get to optics. But basically the idea is you trigger off, see there are 32 detonators. So you have to fire them all off simultaneously. That's hard to do. For the bomb project in the United States, they assigned, turns out my thesis advisor, Louis Alvarez, was one of his jobs is to try to figure out how to make all these detonators go off at the same time. He solved that problem. And so he was responsible for part of the design of the Nagasaki bomb, too. So you get these detonators to all go off at the same time. They begin causing an explosion that goes inward now. But with these shapes, these things that are called the lenses, what you do is you make the explosion go in just such a way that it comes to get together into a perfect sphere just as it's coming in. This is a tricky thing to do. I've seen the places in Los Alamos where they build these things. They have machines that grind the high explosive to make them just the right shape. You have to get them extremely uniform. How do you have someone, machinist, working with this high explosive to grind it just the right shape? What if it goes off? He's dead. So you just say, oh, take the risk? What they wound up doing is they had the machinist half a mile away, working with a video camera, machining this thing remotely in order to machine the high explosives. This is not the sort of bomb a typical terrorist group is going to put together. You get a really high-tech country, such as, I don't know, the United States, Britain, France, Israel, or you get a low-tech country that's willing to give up feeding its people in order to put all of its money into having a small high-tech sector on nuclear explosives, and you pay us, get really top people, and help everybody else, let them starve. So we're talking, of course, of North Korea. Then you could do that too. So this is where you work. But a terrorist group isn't going to do this, in my opinion. This is too hard to do. There are other clever things put in this design. Some of them were classified for a long time. There's something called a tamper. The tamper, it turns out the explosion pushing against the tamper does a better job of compressing it. They have reflectors in here. The reflectors mean that when the neutron does leak out, it bounces back. That was one of the secrets that Heisenberg didn't come up with for Hitler in World War II. He didn't think of the reflector. And as a result, the critical mass that he was imagining would be needed was much, much larger than it turned out was in the nuclear bomb of the United States because of the reflector. His group didn't come up with that idea. But it's in this plan here. What else is in here? They had the initiator in the beginning. Okay, that's polonium and beryllium. And the polonium and beryllium, when they come together in the compression, produce the neutrons that start this thing going. So this is the most elaborate, accurate design I was able to find that's unclassified. The reason that I was able to show you this is simply that this was not a US design. This was a design that was drawn for the Senate by Khalid Hamza, who was the bomb designer for Saddam Hussein. He defected, I think, in 1995. I think that was when it was. Almost didn't get out of the country because the US thought he was a fake. But he was the guy in charge of the nuclear bomb program in Iraq in 1995. You can see why the US intelligence agency drew the wrong conclusion that Saddam Hussein was deeply involved in this. He had done this in 1995 at a time when he claimed to be abiding by the treaty but wasn't allowing full inspections. He never did allow full inspections. That's why it came as a shock to many of us when there actually were no bombs or even components of bombs that we could find in Iraq, because as recently as 1995, his chief bomb designer who defected actually knew a lot about the bomb design, and they were doing tests. So give people a little bit of slack when they say that they were mistaken. There was a lot of reason to think there were bombs being designed there. So we'll be getting back to that. I want to talk today also about nuclear reactors and other things for a reason I'll come to. So these were the two bombs. The problem with making a plutonium bomb is making the implosion work. I want you to know that. That's the difficulty. That's very hard. That's very high tech. And it's a high tech that you don't just get in the typical engineering school. This is a thing where you get really good people, you put them together, they do lots of experiments, They do lots of chemistry and lots of physics, and they figure out how to make it work. And it's not easy, but it was done by a group of scientists in 1945. It was done independently in Russia, in France. It's not, you know, if you have the resources and, you know, a few $1 billion, you can do that. Not easy for a terrorist group to do it. That's the problem with the plutonium bomb. There are two types of bombs. There's the plutonium bomb. Problem there is not getting the plutonium. Problem there is making the bomb out of it. Problem with the uranium bomb is getting the uranium. So let me say a few words about that. You start off with uranium, natural uranium, that you dig out of the ground. Natural uranium, it's actually quite abundant. In granite, it's typically a part per million of uranium. A part per million, how much is that? Well, if you have a cubic meter, a part per million is a cubic centimeter. That's a lot. How much do you need to make it? That's just from granite. But if you go to uranium ores, you find a lot more of it. How much do you need to make a bomb? Well, let me give you the number for plutonium, because that's not classified. You want to know this number? This, by the way, this was an implosion design for uranium, which is, you know, super fancy because you don't really need implosion, but it will work better if you have implosion. And this thing was actually labeled as containing, let's see, it has the reflectors here. Here, 15 to 18 kilograms. 15 to 18 kilograms. Well, let's see. Density of uranium is about 15 to 18, something like that. So 15 to 18 kilograms would be 1 liter. 1 liter of uranium, like a quart of uranium will do it. Plutonium is smaller. A cup of plutonium will do it. A cup of plutonium. That's the critical mass. A cupful. That's because you get 3 neutrons out. So how do you get this uranium? As I said, it's not hard to get the uranium. You can do it from granite. Nobody bothers. You go to uranium ores. But then what you get is natural uranium, which is uranium-238. Uranium-238 is 99.3%. And then the uranium-235, which is mixed in with it, is 0.7%. How do you... Now, if you keep them mixed, it will not work. The reason it won't work is very important. When the chain reaction starts and these neutrons fly off, most of the neutrons will be grabbed by the uranium-238. And when they do that, you don't get the fission. Actually, what happens when a neutron hits uranium-238 is an interesting thing. It turns to uranium-239. Uranium-239 decays. And then it decays again, and you're left with plutonium. So, a neutron on a uranium-238 gives you plutonium-239. There are a couple of decays that take place in the process, but that's what you get. This is how you get plutonium. You get plutonium by making it from uranium-238. We'll be coming back to that over and over and over again. You'll be seeing that. So you start with natural uranium. If you can make the chain reaction going, you can manufacture plutonium. If you want a bomb, you manufacture plutonium and then you extract it. We'll talk about that. That's called reprocessing, a word you'll have to know, but I'll come to that in a moment. If you want to extract the uranium-235, it's hard to do. Lawrence, after whom the Lawrence Berkeley Lab was named, came up with a way of doing this during World War II. He thought, and we'll talk, you know, this is, he uses an electromagnetic method. The idea was you build a big tank, you vaporize your uranium, you ionize it so it has a charge, you run it through a magnetic field, and it turns out the uranium-235 will bend in the magnetic field a little more than the uranium-238. So here's the 235, here's the 238. So then you take this plate and you scrape off the uranium-235 and you do it again. And he did this, was able to produce a little bit of pretty pure uranium-235s. Did that here at Berkeley. This thing was not a cyclotron, which is what he got his Nobel Prize for. He had to come up with a name for it. So he decided he would honor the University of California and call it a Cal-utron, named after our university. The thing worked well, and so General Groves had dozens of these things built in Oak Ridge, Tennessee, where by 1945, summer of 1945, they had separated out enough uranium for one bomb, which they put into the Hiroshima bomb. They never tested it, and dropped it over Hiroshima, killing 50 to 150,000 people. Named after Cal. Take that. I don't know whether you're proud of that or ashamed. I don't care. That's the history. At the same time, Enrico Fermi at Chicago was frantically trying to build something that became called a nuclear reactor. And that's what most of this lecture is going to be on, to make plutonium. After the war, the calutrons were basically not good ways to make uranium. They started using different things. They tried gaseous diffusion. The real secret of gaseous diffusion was classified until recently. But the gaseous diffusion plants in Oak Ridge, Tennessee were huge. We produced enormous amounts of uranium with buildings that were a mile long. That's the size of these buildings. And they were gaseous diffusion. What you do there is you heat up the gas. You take uranium, mix it with fluorine, make uranium hexafluoride. You don't have to know these details, but you'll come across them in the news. They talk about North Korea, no, I guess it's Iran having uranium hexafluoride. And we don't even like them to have uranium hexafluoride. Uranium hexafluoride is a gas. You don't have to heat it up very much to have it into a gas. And then by running it through the magic material, it turns out that because the light elements move faster, thermal physics, right? The light things at the same temperature, the light ones move faster. You run them through this magic material. You need a material that doesn't corrode. Uranium hexafluoride is very corrosive. You need something that can stand this stuff. And they had just the right magic material to do that. Its name today is Teflon. It was the high-tech material of Oak Ridge that was used for gaseous separation of uranium. The fact that it was used that way was kept highly classified. Eventually, the space program started using Teflon, and the public caught up. Oh, Teflon, isn't this great stuff? And there's still an urban legend out there that one of the technical results of the space program was the invention of Teflon. Well, it was invented actually before World War II, but its first big commercial use was to separate uranium, using the fact that uranium-235 moves faster, and so it comes out the end first. Subsequent to that, they came up with a centrifuge. Again, it's a gas centrifuge. Now, you'll hear a lot about centrifuges. Centrifuges are basically spinning tubes in which the heavier uranium hexafluoride, tends to go to the outer part. They spin these things very fast as they can. To make it work well, you have to go super fast. I mean, the edge of this thing is going a kilometer per second. That's how fast they're spinning. You need the strongest possible materials. And so they came up with this material called miraging steel. You'll read about that too. Miraging steel, as far as I know, only has two commercial uses. One of them is for centrifuges, for uranium. The other is for golf clubs. Someday they'll use it in tennis rackets and other things too, because this is where all the high tech goes to these days. It goes to people who are willing to spend $300 for a golf club. And if you have a steel that's stronger and harder than anything else, hey, you'll find some wealthy people. Well, you know, golf is played by team members at Cal, but what really supports golf is a large number of, I think, wealthy people who buy miraging steel golf clubs. Anyway, North Korea seems to have a real interest in golf clubs or centrifuges. Can't really tell which. Once again, they have a tube that spins really fast. I visited one of these centrifuge plants, and it's really impressive. I mean, it's smaller than this room, and it has these tubes in there, and it will separate out enough uranium every day for a bomb. And you walk into the room, and the thing is operating, and you listen. You don't hear a thing. Why not? Because these things are so well balanced. They have to be well balanced to go that fast or they'll just rip themselves apart. So they have them exquisitely balanced. The design of how you build that is really highly classified. A few people have figured it out. There was a Pakistani scientist, A.Q. Kwan, who had the designs for this. He sold them to Libya and to North Korea. And has gotten a great degree of infamy for having done this. We found out about it because Libya decided maybe it makes more sense now that the Soviet Union is not around to be friends with the US instead of enemies. So they decided they would stop trying to make an atomic bomb. We'll open up, show you everything we have. We go in there and say, oh, these are interesting designs. What's the signature A.Q. Kwan here down at the bottom? Khan. And he was traced to Pakistan. He was their chief bomb minister over there, and so he was thrown out, and then basically his sentence was commuted by the president, so he gets no punishment. I suspect the reason that happened, this is not physics, I'm just giving you idle speculation now, is that of course he didn't do that on his own. It was the whole Pakistani government who was doing it. And so he wasn't really responsible, but the Pakistani government wants to come across as good guys, so they had someone to blame. But anyway, that's the gas centrifuge. There are other advanced ways, too. There's the laser enrichment, which has actually been accomplished at Livermore, but doesn't seem to be. And the whole idea here is to turn 0.7% into 90, 95, 100% uranium-235, because otherwise it won't work in the bomb. Now, a little story. There was lots of reason to think in 1990 that Saddam Hussein was designing nuclear bombs. I mean, it turned out he was, okay. But people forget this because they confuse it with what happened in 2000. In 2000, we thought we were going to go in there and find all of his bomb stuff, and there's nothing there. He had dismantled it. And so people say he wasn't doing it, which is true. But in 1990, he was. And people had been searching, and people sometimes, oh, by the way, people forget that President Clinton bombed Baghdad in 1998. Bombed Baghdad in 1998 to destroy the nuclear facilities that he was suspected were there. That was in 1998. A little bit more of history that we tend to forget. He thought there were nuclear things going on there too. But part of the reason was in 1990, we had searched for every possible thing. We had looked for gas diffusion plants. Had some suspicious looking things, but gas diffusion plants were big and they really didn't fit. Gas centrifuges, that was the way to go. He was probably doing gas centrifuges, looked around, but gas centrifuges are so easy to hide. They fit in rooms smaller than this. They're high tech, and so you try to look for people who are sending in raging steel, but you could use other types of steel. So there was no clear gas centrifuge plant. Laser enrichment, he didn't seem to have the right kind of scientist to do laser enrichment. So it was a big mystery. If he's doing a bomb program, what is he doing? Anyway, Saddam Hussein invaded Kuwait. The US went in, retook Kuwait, decided not to, well, actually reached an accommodation with Saddam. They would not invade Baghdad. They would leave him in power in return for detailed and complete inspections. Back then, he allowed the UN to come in and give detailed and complete inspections. And what came was a shock to me. He was building devices to purify uranium. The UN found them. I have a photograph. It wasn't gas diffusion, it wasn't gas centrifuge, it wasn't laser enrichment. Here's a photograph. The UN found these devices. They were for uranium enrichment. It destroyed them. This is one of the blown up ones. Blown up by the United Nations. That's actually a calutron. The primitive technology that was used in World War II and then abandoned because there were so much better ways to do it. But Saddam Hussein, with his limited resources of only, a few $billion he could spare, and his limited scientific expertise, had gone back to the easiest way to do it, the way Lawrence had done it, named after your university. Saddam Hussein built calutrons. As near as we can tell, he did no major enrichment of uranium using these calutrons. But here's a calutron, one of Saddam Hussein's calutrons, that was destroyed by the United Nations when it was found in 1990. I'll leave that up. It's a pretty picture. No, I'm going to come back over here now and talk more about other things. So this is the story of nuclear bombs, and we're going to be talking more about this too in the coming 2 lectures. But what I'd like to do right now is move on quickly to nuclear reactors. And the reason is that tomorrow I'm having a minor operation. And so when I come in on Thursday, I'm not supposed to be too vigorous. I'm not supposed to bounce around because I will have probably an eye patch. They're going to go into my eye and remove a film that's been growing in there. It's kind of fun. And it is interesting. I mean, I was at the doctor's office last week, and he said, so do you want to be awake or asleep during the operation? I said, oh, awake. I wouldn't want to miss this. It was in the reception room, and people turned around. You know, everybody likes to sleep during these things. I like to see what's happening. And boy, when they're operating on your eye, you really do see what's happening. It's really... So those of you who gross out on this, close your ears right now. Because what they do is they're going to give me local anesthesia. I don't want any sedative or anything, just local anesthesia. And then what they do is they stick these needles in. I said, close your ears, come on. And there's a little film growing on my retina. And what they're going to do is peel it off and then suck it up and then pull the needles out. It's really a minor operation, but it's supposed to give me much better. Right now, I have great vision in this eye. I'm going to try to get better vision in this eye. Anyway, interesting. So that's going to happen tomorrow. Now, I hope to be in here on Thursday. But what I'm going to do on Thursday is show a film that I had intended to show next week. I'm going to show it on Thursday because of this operation. And it's a film about nuclear reactors. Very important film for you to watch. So let me now spend the rest of the lecture talking about nuclear reactors in preparation for this. So what is a nuclear reactor? This is what Enrico Fermi was doing in Chicago while Luis Alvarez was in Los Alamos and other places. Here's the way a nuclear reactor works. What you do is you take uranium and you take ordinary, natural uranium, unenriched. That's what Enrico Fermi was doing. Unenriched uranium, and it doesn't work. It doesn't work because the uranium-238 absorbs the neutrons. But this is what they figured out. If you surround it with carbon, and you put it in little pieces, so when a fission takes place, the 2 neutrons leave, and they don't run into any uranium-238, because that would absorb them. That's bad. But they leak out into the carbon. Carbon, it turns out, doesn't absorb neutrons at all. The neutrons bounce off the carbon. The carbon picks up a little bit of energy. It heats up. And the neutrons lose energy, so the neutrons slow down. This carbon is called a moderator. And the purpose of the moderator is to slow the neutrons. Now, so these neutrons slow down after a bunch of bounces. And at some point, they will actually hit their uranium again. And what they had discovered is that slow neutrons are not absorbed on uranium-238. They're just a little bit. So if you slow down the neutrons with a moderator, you can still get a chain reaction. What they really wanted to do was not really get a double, 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 because this thing would blow up. What they really wanted to do was get, on average, one of the neutrons. So you want one, you get uranium-235 is fission fragments, typically 2 fission fragments, plus 2 neutrons. One of those neutrons you want to hit another uranium-235. The other neutron you'd like to hit uranium-238, making plutonium. So this way, every fission leads to one more fission. So once this thing gets going, it just keeps on going at the same level. It doesn't get bigger, 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 and explode. That's what a nuclear reactor is. So a nuclear reactor is, it has a moderator. That's the real key. The moderator means you can work with unenriched uranium. There are other moderators you could use. In the United States, we tend to use water as a moderator. Okay, water as a moderator It won't work with unenriched uranium. You have to have 3% uranium-235. So we use slightly enriched, what's called reactor-grade uranium. That's produced at Oak Ridge. So this is the idea. This is the basic idea, and I'm going to be talking primarily about two different designs. One of them is the carbon design, the other is the water design. In the United States, most of our power reactors have these tubes coming down into water, and this whole thing is in a big vessel full of water. And other than that, the neutrons come out, they're slowed down, they come back in, and one of them on average produces a plutonium, and one on the average produces another fission, so it keeps on going. In the beginning, you set it up so that you produce double, 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 double until you get the level you want. And then you put in control rods that absorb neutrons that make this thing keep in a steady state. So here's a key thing to remember about the nuclear reactor. In a nuclear chain reaction in a reactor, you're not doubling anymore. You want to keep it going at a constant rate. You make this plutonium, and then every once in a while you pull these things out, and you separate out the plutonium. Okay? So that's called reprocessing. You've got to know this word. You'll see this in the news all the time. That separates the plutonium. We allow many countries around the world, by treaty, we give them nuclear reactors. We give them the uranium that we made in Oak Ridge. Their part of the bargain is that they give us the fuel when it's finished. So we can separate out the plutonium and they don't get it. So in exchange for giving them nuclear technology and giving them the uranium, we get back the plutonium. We don't want them to have it because then they could build a bomb. When Iran says we are no longer allowing inspection of our facilities, we are turning off the cameras. The UN can no longer watch us. The reason we fear that is they now can take the material out of their nuclear reactors, remove it without us knowing, reprocess it, and get plutonium. A friend of mine, Mike May, went to North Korea so that they could demonstrate to him that they had done reprocessing, and they handed him a piece of plutonium. He said, "Can I take it out of the jar and feel it?" They said, "Sure." Took it out of the jar, could feel the plutonium. It was warm. It was about the right warmth for plutonium. Wasn't he worried about the radioactivity? No, because he knows you've got to breathe this stuff in for it to be dangerous. So he wasn't worried about that. He washed his hands afterwards. But he wasn't really worried about, but he could tell it was warm, about the right warmth, because he had worked with plutonium before. So North Korea is doing this reprocessing. Reprocessing means you go into the reactor and you remove the plutonium. Now, what's the big deal about nuclear reactors? So let me talk about that now. Let's talk about reactor accidents. About what happened at Chernobyl, what happened, what is it that people worry about? Question there. Why couldn't terrorists blow up one of our reactors? Boy, I sure hope they try. I really hope they try. There's a whole story behind this. I don't want to digress right now. Maybe I'll go into that on Thursday or next Tuesday. I've actually visited a nuclear reactor down in Southern California with a counter-terrorist group. The counter-terrorist group had planned an attack on the reactor. And they went down there because I went with them because the people who were defending the reactor had their counter plan. And the question was, how would it really work if they came in and tried to invade this reactor? Would the plan really work? And I was just as impressed as hell with the details of this, how they had protected this reactor against an attack. They did such a good job that I realized, boy, if you're a terrorist, you want to blow up an apartment building in Chicago using natural gas, you don't want to go after a nuclear reactor. It's so much easier. So there's a long story on that, but let me that's the quick answer. Yes?
In those treaties, when you're giving them uranium-235, could they just give that to the bomb?
Well, you don't give them fully enriched. You give them 3% enriched. And that you can't use that for a bomb because you won't get a chain reaction. The uranium-238 is there. This is getting to the issue of the nuclear explosion. In order for something to go off like a nuclear explosion, you can't have the uranium-238. But wait a minute, you can if you have a moderator, right? So maybe this thing will explode like a nuclear bomb. No, this cannot explode for a nuclear bomb for the same reason it works with unenriched uranium. This is a tricky thing. Really wake up now and pay attention. Everybody. There's a key thing here. In order to work with reactor-grade uranium, only 3%, you have to have the moderator. Otherwise, the uranium-238 eats up all the neutrons. If you have a moderator, you have slow neutrons. That means the chain reaction is slow. It comes out, it wanders around, and then it finally finds another uranium. Boom, out comes two of them. One of them goes to plutonium, the other is wandering around. Finally, it's a slow thing because of the moderator. Because it's slow, suppose you start to overheat. This happened in Chernobyl. In Chernobyl, they had a graphite reactor, a very badly designed graphite reactor. It started to overheat. It had a positive temperature coefficient. Nothing like that would ever be made legal in any country that had any kind of oversight. Positive temperature coefficient means that when it gets hotter, it starts reacting faster. That's absolutely illegal in the United States and every other rational country, but it wasn't in the Soviet Union. So the reaction started going faster and faster. It still had the moderator, because without the moderator, it wouldn't work. But it got going so fast that it got up to the energy density of TNT. Now, at that point, in the atomic bomb, the reaction is going so fast, because it has fast neutrons, that before the thing can blow itself apart, the reaction doubles, and you've released all the energy of all the atoms before the thing can throw itself apart. In Chernobyl, once it got up to the density of TNT, the thing exploded, and we never got a nuclear explosion. You can't get a nuclear explosion. You can't get the factor of 1,000,000 if you have slow neutrons. But you need slow neutrons, or the reactor won't work at all. So what happens in these things is the Chernobyl nuclear reactor blew up like as if it were loaded with TNT. There was an explosion, but not a nuclear explosion, not an atomic bomb type explosion, just a pure dynamite explosion. Well, what's so bad about that? Well, 36,000 people dead is what's the result of that. Why is that? Because it's not the explosion that killed people. What happened is the explosion set the graphite on fire. And the graphite started to burn. Now, what's the problem with that? What's the big deal about a fire? The problem is all these fission fragments that are in these pellets. They're highly radioactive. Those are the things you want to take out, and you'd like to remove the plutonium from them. You'd like to bury them underground somewhere, but instead they go up in the smoke. So this highly radioactive stuff is going up in the smoke. And that's what then spread over the city of Chernobyl and all the way up to Sweden. And when you calculate it, as I said, you'll never see these deaths because they're a tiny fraction of the other cancer deaths. But we calculate 36,000 real people, each one of whom is probably a nice person, and they're dead because of this. They would have lived longer. So it's a real tragedy, 36,000 real deaths. And it came about because of a reactor accident that ran away. It would never blow up like a nuclear bomb because it uses moderated neutrons. If the neutrons aren't moderated, then the chain reaction stops because then they're absorbed on the uranium-238. We can't have both. To make it work with slightly enriched uranium, reactor-grade uranium, you have to use slow neutrons. If you use slow neutrons, the thing can't explode. Well, it can explode a little bit, enough to set the thing on fire and spread this radioactivity. That's what happened. What do people worry about for the American reactor? You're not going to have a carbon fire. Probably you're not going to have a reactivity accident. Reactivity is when it starts getting hotter and it gets worse because it has a negative reactivity. If this thing overheats, it tends to slow down the nuclear reaction. So what do people worry about? They came up with what they call the worst case scenario. Worst case scenario. And the worst that anybody could come up with is a nuclear meltdown. And let me show you how the meltdown works. This is the idea. Somehow a pipe breaks and you develop a leak in the reactor. And this water all flows out. What's the first thing that happens when the water flows out? The chain reaction stops. Why does the chain reaction stop? Because there's no moderator. Without a moderator, the chain reaction. So the first thing that will happen in this worst case scenario is the chain reaction stopped. By the way, in the Chernobyl, once this thing had the explosion, the chain reaction stopped. 1985, was it? 86? The Soviet Union was in the beginning of the era of glasnost. I had been there shortly before that and had made 4 trips to the Soviet Union. The glasnost thing was very exciting. They were doing their best to be open like the US was. And they announced that they had this accident and the chain reaction had stopped. And the head of the Senate Intelligence Committee at that point said, another blatant lie from the Soviet Union. Anybody who knows anything knows that chain reaction hasn't stopped. And I start crying. Part of the inspiration for this course. If any of you is ever head of the Senate Intelligence Committee, you will know that they weren't lying. Here he is publicly accusing them in front of the world of lying, and everybody who knew anything technical knew that he was wrong. Of course the chain, so why did he say that? Well, he was probably confusing the chain reaction with the radioactivity of the fission fragments. Of course there's a lot of radioactivity in there. Everybody knows that doesn't stop, and that's the danger. But the chain reaction had stopped, which is all that they had said. So the radioactivity continues on. Now, once the water is all drained, these things are full of radioactive particles. So what happens with them? Well, they're hot because they're radioactive. The water was cooling them. In fact, that radioactivity contributes to the heating of the water. This water is made hot, and that's what goes and runs the turbines, the hot water. The chain reaction is used to heat water. And the water runs a turbine. That's how a nuclear reactor works. So what happens when the water is all gone? You're left with the fuel. The fuel gets hot. It might melt. So they put in a very carefully designed emergency core cooling system. This is called the core cooling system. And that cools it off, so there's no problem. Well, if there's no problem, then this is not the worst case scenario. So therefore, let's assume the emergency core cooling system fails. After all, we're trying to get the worst case. What's the probability it will fail? Well, you can calculate that. It's infinitesimal. But, people make mistakes in these calculations. They don't realize things. So let's do the worst case scenario. By the way, I believe in the nuclear industry, that's the only industry in which we require a worst case scenario. You have to assume that everything fails and then ask what happens. We don't do this in the chemical industry. Worst case scenario in the chemical industry, a truck full of chlorine driving right through a populated area of New York City and crashes and the fumes come out. Every now and then you see a train crash and they evacuate the nearby cities because the trains carried chlorine or something like that. But nobody analyzes worst case scenarios. But in the nuclear industry they do. People are beginning to catch on to this. And so now there's a movement among those of us who are truly worried about greenhouse gases and carbon dioxide, which we'll be talking more about later in the semester, that maybe nuclear power is actually much safer for us than gasoline and coal. And so there's some nice op-ed pieces by Nicholas Kristof, for example, a rather liberal columnist, entitled "Nuclear is Green." So there may be a mood shift in this. But let's go on with the worst case scenario. So therefore, the water's gone, the emergency core cooling system fails, this stuff just heats up. What happens when it heats up? Well, it will melt. So nothing's working, the stuff will melt, it'll dribble down and form a little puddle on the bottom. Now this stuff has rather thick steel. I forget exactly how thick it is. I think maybe a foot or two of steel. And it's inspected all the time to make sure there are no cracks and things. But worst case scenario, let's say this pool happens to accumulate in a nice small area and it melts its way through and dribbles out the bottom. What happens then? Well, this whole thing is surrounded by a concrete containment building made of reinforced concrete. I forget again exactly how thick that is. I used to know these numbers. But it's probably 8 feet thick or something like that. Chernobyl had no containment building. None. This has the steel, and then it has the concrete. So it gets to the bottom, it should spread out and cool off, but what if it doesn't spread out? What if it somehow manages, worst case scenario, to come down and work its way through the containment building? Liquid stuff. If you ever saw it was the first Alien movie where they snip off this alien that's on the guy's face, and out comes this acid that starts melting its way through the spaceship all the way down. So maybe this stuff will do the same thing, worst case scenario, and continue on down. Then what happens? It gets into the ground. Okay, big deal. The gases can still escape. And there are some gases that can escape and lead to bad levels of radioactivity if that happens. So this is what people analyze. This is called the nuclear meltdown. The movie The China Syndrome was about this. The scenes where they say, meltdown. What does that mean? It means we're all dead. The connection to that logic I never understood. But this gas can escape and spread over the countryside, and it's a bad amount of radioactivity. Is it as much as Chernobyl? Oh, no, nowhere near as much as Chernobyl. Why not? Well, first of all, it's only the gases that get out. The rest gets into the ground. Oh, that might get into the groundwater. Yeah, but the difference between getting into the groundwater and having come and smoke and cover the city. So this worst case scenario is not nearly as bad as Chernobyl. Chernobyl was worse than we can imagine possibly happening with a decent design. I was in Cuba a few years ago, and there was a little tragedy there because we visited one of their villages, one of their cities in the south, where they had a nuclear reactor. And they were dismantling it. A country that is desperately poor were dismantling their nuclear reactor. Why? It turns out it was given to them by the Soviet Union. You know what kind of design it was? It was an exact replica of the Chernobyl nuclear reactor. Once the Chernobyl nuclear reactor went, nobody in the world would ever run one of those things again. This thing was just regarded as such a bad design once this had happened that even in a poor country like Cuba, they felt they had to dismantle this, give up the electric power that they would have come from this billion-dollar investment because of the design. Now, how deep will this thing go? Well, you've heard of hospital humor. You know, you can look on the web, and if you have a friend who has cancer, as I do, he wanted to know if I knew any cancer jokes. So I look up on the web, cancer jokes, and you find these huge compendium of cancer jokes. These are jokes that cancer patients tell each other. So every area has its humor. In this thing, the humor is, where will this thing stop? And the joke is, when it gets to China. Right? All the way down through the center of the earth. I mean, of course it wouldn't. It would stop in the center of the earth because then the gravity goes the other way. But so this thing got the name the China Syndrome. The nuclear meltdown, where the stuff is headed to China, but enough leaking out so that Jane Fonda can panic and think she's going to die. That's in the China Syndrome movie. Is called the China Syndrome. I want you to know this. This is what people worry about. Now there are other things they worry about too. Once you've had this thing operating for a year or two, these things are full of radioactive fission fragments. The ones that decay right away, those are fine. They give you more heat. You use that heat to heat the water and run the reactor. But after a while, you're left with the things that live for 50, 80 years, something like strontium-90. And that's not decaying enough. And you've used up your uranium, so you pull out the rods and put in fresh uranium. You've used up most of the uranium, and the decay heat isn't doing you much good. So what do you have now? You have a rod that's full of plutonium and fission fragments. So what do you do with this? Well, many people, like in France, think the right thing to do is you take the plutonium and you separate it out. That's called reprocessing. So reprocessing is a word I want you to know. Reprocessing. In fact, there it is, reprocessing. That's removing the plutonium. And then the plutonium can also be used in a nuclear reactor. It's a fuel. You put plutonium in instead of uranium. And so that's what many countries do. We decided back 30 years ago not to do that. Instead, this plutonium stuff would be considered waste. And so we decided we would bury it instead of reprocessing it. Why did we decide this? If you go back into history, I've tried to figure this out, and there are people who will tell me and give me their opinions. But I think the reason was that in those days, uranium was cheap, weren't about to run out. Plutonium had a bad name. People thought it was far more dangerous than it really is. And of course, you could make bombs out of it. There was discussion back in those days of something that was called the plutonium economy. There would be so much plutonium around from reprocessing that people would start using it maybe to heat their homes or something like that. And there was a very strong reaction against this. We did not want to go to a future that had a plutonium economy, and so it was declared that we would not reprocess. Instead, we would keep it as waste. Because waste is no problem. You just bury it underground. These days, there's a great political uproar against burying plutonium underground. Why? Because it has a half-life of 24,000 years. So it'll keep on decaying for 24,000 years and even longer. That's only its half-life. And so now they don't want, there are people who object to burying the waste. There's a special place in Nevada called Yucca Mountain, which was a place that has fewer earthquakes than almost anywhere else, Yucca Mountain. They build these tunnels underground to store this stuff, and now people are objecting it's not safe enough to put it there unless you can guarantee its safety for 24,000 years. And hey, you know, by that time, the Democrats will be back in charge of the White House or something, I don't know. 24,000 years, how can you guarantee that? Therefore, you shouldn't put it in Yucca Mountain. My reaction is, what do you mean you shouldn't put it there? So where are you going to leave it? We have this waste. You know where it's sitting? It's sitting next to the nuclear reactors in a separate building. And one of the things I was most worried about is not a terrorist going after the nuclear reactor, but a terrorist going after these temporary waste sites that are right next to the nuclear reactor. Why? Because it's not safe enough to bury them a mile underground. So let's leave them in a building next to the nuclear reactor. And people say, no, neither of them are good solutions. But the stuff doesn't go away. So you need to put it somewhere. And what about transporting it? Is there a danger in transporting it? Interesting story there. Because what they decided to do is they decided to make it so safe in the transportation that nobody would worry about that. Now, the people here who are in psychology may appreciate this story. If you decide you're going to make it so safe that nobody will worry about it, you wind up really frightening people. What they do is they put in these big concrete containers on big trucks. And it's so safe that you could blow it up with dynamite. And the truck will be destroyed, but the container sits there undamaged. They prove this. So what do? They have a nice cliff, and they take the truck full of this nuclear waste, and they drive it off the cliff. They even load the truck with dynamite and gasoline so that as if it was sabotaged in some way, this thing goes crashing down to the ground, the thing blows up in a big fireball, and there is the undamaged container. The public sees this, and they go crazy. They associate death, destruction, explosions, everything with nuclear waste. Nobody wants explosions like that in their highway, in their town. So the psychology was done completely wrong. And as a result, there's a great uproar now against transporting it for just that reason.